my previous line integral example was popular, but not very interesting. So I just picked some strange vector field, and I want to do a line integral as another example for one that's a little bit more complicated, just for fun. So I made this vector field up, I made it up, and I printed it out. I made this in Python. I'm gonna make a tutorial about how to make these graphs. It's really actually pretty easy. And so here's my vector field x hat minus x y hat. I don't know where it came from. It doesn't mean anything. And I want to go from x is 0 to y2 down to here to 0. So I want to integrate that. Okay, so I'm going to use Cartesian coordinates. And you can see we get this weird shape pattern of field, but it doesn't really matter. So I'm going to call the line integral I. So I'm just going to say this. So let me write that again. I feel like my camera's off. I feel a little off. I think I moved my camera a little bit, but that's fine. Okay, so I'm going to write f is x, y hat minus x hat minus y hat. And then I is going to be the integral from point A to point B of f dot dl. That's the line integral part. Now, if I'm using Cartesian coordinates, then dl is the vector dx x hat plus dy y hat. And I'm going to go ahead and let you know, I'm going to do this and along that path, and then I'm going to do that path in Python. I'm thinking about doing a circular path too, but that's a little bit more complicated, so let's just see how it goes. Okay, so if I do this dot product, I can do that. I get I equals the integral from point A to point B. I just take the dot product. Here's f, here's dl, so I get xy times dx, xy dx, and then I get minus x dy. And that's a sum, so I can actually write that as two integrals. So it's going to be the integral from A to B of xy dx plus the integral from A to B. And I'm leaving these A and B's generic because they actually have limits, but you'll see how in fact it comes out, of negative x dy. And so here I have a problem. I have a problem because this integral, the integration variable is dx. So this is from x equals 0 to x equals 2, and this is y. So it's from y equals 2 to y equals 0. But I have a y here and I have x there, so I need to get rid of those. And I get rid of those by looking at the path. So let me draw my path right here. I'm going from this point A to this point B. And they're symmetrical because I was going to do a curve too, but let's just, I'm still thinking about that. Okay, so what is this path is a line. In 2 dimensions is really not too complicated. If you want to do a 3-dimensional line integral along a path, then you have to use some parametric equations, and I just didn't want to do that. So what's the equation of this line? Well, I can say this. Y equals mx plus b. And so what's the slope? What's going to be the change in, the slope is going to be m is going to be delta y, which is going to be the final 0 minus the initial 2 over the change in x, 2 minus 0, so I get negative 2 over 2 equals negative 1. And what's the intercept? Well, I can look at, I just actually have a point right there. The intercept is y equals 2. So I say y equals negative x plus 2. That's my relationship between x and y. So right here, when I have a y, I can put in x, negative x plus 2. Right here, when I can solve this for negative x equals y minus 2. Just solving this for negative x, put that in right there. So now my integral becomes I equals the integral from x equals 0 to x equals 2, x times y, but then I'm going to put this in for y, negative x plus 2 dx. That's all just depends on x. I can actually integrate that. Plus the integral from y equals 2 to y equals 0, and I'm going to have negative x, which is just y minus 2 dy. Okay, let's just multiply this out. This is actually pretty easy to integrate. So let me just rewrite that integral, those two integrals. I equals 0 to 2. This is integrating over x. I have negative x squared. I'll just leave it like that. Plus 2x dx plus the integral, that's the integral, 2 to 0 of y minus 2 dy. Okay, so now I can use my integration here. The integral of negative x squared is going to be equal to negative x cubed over 3. The integral of 2x is going to be x squared. And I evaluate that from 0 to 2. And right here I have plus y squared over 2 minus 2y evaluated from 2 to 0. Okay, so this is going to be, I'm plugging in the 2. I get negative 8 over 3 plus 4 minus 0, 0. And then I get 0, 0 minus 2 squared over 2, which is 2 squared is 4 over 2 is 2. And then I get plus 2 times 2 is 4. So this is going to be equal to negative 8 over 3. And then I have plus 6. And that's going to be negative, is it 8 over 3? Yeah, 8 over 3. Yeah, 8 over 3. Let's just leave that as plus 6. It's just a number. Okay. So that's that. Let's do this now in Python. Okay. I'm actually going to modify my program. I already did this before. So let me just pull up the program. I forgot to pull it up. I wasn't thinking. Don't save that. Don't save that. Let's see. Last updated. Line integral example. Okay. So I have it. Let me switch over. Okay, so here's my line integral example. This is for a different vector field. Let me just tell you what I did. I had points A. I wanted to go from A to B, but then I add a middle point so I could take a different path. So let me just run this. So this goes from point A, negative 2, negative 4, up to here, 2, 0, 0, up there. Yep. And then I took this other path going along that curve, which I'm partially blocking, but it's fine. So let's just change the stuff that we need. I'm going to change first A and B. I need to make a new copy of this. Okay, so let's change A and B. In this case, my starting point is going to be 0, 2, 0. And my ending point is 2, 0, 0. Right. And then C, let's just leave that, doesn't really matter. G1 is a graph. FP is the second plot. This is just the starting and the ending points right there. F1 is the other path. Okay, this is my vector function. I defined it as a function. Here I had x, y. I'm just going to change this to what I have, which is x times y in the y direction minus x in the y direction. That's what I had, right? Yep, okay. N is the number of pieces I break it into. Is that too small? N is the number of pieces I break it into. L is the vector from the beginning to the end. And DL is that tiny little step vector, right? I'm moving a tiny distance. And this is one of the big things, this difference between an analytical line integral and a numerical line integral. In an analytical line integral, my element is dx dy. It's dx x hat dy y hat. That's it. I don't have to worry about the direction. All that's taken care of in the limits of integration. But here I actually have a vector. I have a tiny little vector, and I'm going to assume the vector field is constant over that length, and then it's going to take the dot product. Okay, so now this is the first line integral. All I have to do is, while I have my position R, that's where it starts, and I'm going to move all the way to to B. And I is my integral, because I need to, each piece I'm going to add up. I feel like I'm not doing a great explanation here because I already explained this and I should have started from scratch, but I will link the other video down below with a much better explanation. So during each segment, I'm going to calculate the integral f.dl, and I'm going to assume f is constant. And I'm going to add that to all the other pieces, but I need to start with something. So I is 0, and then I'm going to calculate all the pieces and add them up there. Okay, so I'm going to do this while the x position of my position is less than my b position. In this case, it's going to work, right? Because I'm definitely moving to the right. And if it was not doing that, I would have a problem. But other than that, this line, 23, that's still the same. I didn't have to change anything. This one's the same, that one's the same, that's the same, everything's the same. I'm going to comment out everything else. And this is the Python, the GlowScript v Python comment. You can just do three single quotes. Okay, let's see if this actually runs. Oh, did I print it? Yeah, I did. Okay. And something happened. Okay, vector requires 3 arguments, x, y, and z. 3? Which line is that in? Vector requires 3 arguments. Oh, here. There's return that. Okay. Now run it. Okay, there's that. I got a value. Let me do this. Print IA equals, this is the other version. I said it was -8 divided by 3 plus 6. Let's just see if that's the same thing. If it's the same thing, I'll be pretty excited. Check that out. Okay, now let's do just like we did before. I'm actually going to go from 2, 2, straight across and then straight down instead of taking an angle. So to do that, I need another point up here. My third point, which is in the middle, instead of going from, I'm going to go straight from 0, 2 to 2, 2, and then down to 2, 0. So let's just put this at 2, 2. And then all this other stuff, I don't know that I need to change it too much. Get rid of that. Let's see. And I could have done this on paper. And I should have done that on paper, but I didn't. I was too excited. I was thinking about the circular thing. Okay, so here I still have n. I'm going from, that's the first one. And then I'm going from A to C, which is the middle point. And then I'm going down to, that's fine. So while r, this is not going to be, that's fine. While r dot x is less than c dot x. And then that's all fine. And I don't need to print I, because that's the intermediate I. And then I'm going to go from B to C. And in this case, I commented out the initial conditions. I don't want to reset my counting variable I to 0. I want to keep adding on to it. And let's see, while r dot y is less than this. See, I'm going down. So this should be while r dot y is greater than b dot y, because I'm going down. Okay, and that should work. And print I path 2. Let's do that. Let's see if it works. Okay, now what you see here is that the path integral is different. I get a different integration for a different path. That means this is not a conservative field. Okay, technically, if you get 2 different paths and you get the same line integral, it doesn't mean that it is a conservative field, because maybe just those 2 paths worked. But in this case, if you get 2 that are different, it's not a conservative field. Okay. I don't think I'm going to do the circular path because it's not a conservative field, so it wouldn't be great to show. I think I might save that and do another example. But I could do... I think I'm not going to. I think this, along with my previous line integral example, is pretty thorough. So I'll leave it at that. And then maybe sometime in the future I'll do another line integral video. But hopefully this is useful. The code will be down below. The link to the previous video down below. Let me know if you have any questions.